The great idea that Feynman and Deutsch had that led to the idea of a quantum computer was, well, if nature is giving us this computational lemon, then why don't we make lemonade out of it? I like to argue that P versus NP is maybe the most important unsolved math problem, and my argument for that is that if P equaled NP and the algorithm were fast in practice, it would mean that you could ask your computer to solve all of the other great open math problems for you. Unfortunately, we now see unbelievable amounts of hype, right? The startup companies in this space learn that they can raise lots of money and get lots of people excited by just saying, we can use a quantum computer to do financial portfolio planning and neural nets and all these other things that you're excited about. And they don't even notice the question of, is there any advantage over a classical computer?
In this episode of the 632 Nanometer podcast, Mike and Misha sit down with Scott Aaronson, quantum computing pioneer, theoretical computer scientist, and complexity class connoisseur. Scott takes us deep into the heart of computation, what it means for a problem to be hard, and how this concept of hardness underpins modern cryptography. They discuss how quantum mechanics might, or might not, give us a computational edge. And Scott explains how quantum computers leverage interference to generate speedups. Along the way, they touch on machine learning hype, quantum supremacy, the Carl Lipton hypothesis, quantum money, and whether the laws of nature are already the ultimate algorithm.
I found an interesting fact from Wikipedia, which says that you taught yourself calculus at the age of 11, provoked by symbols in a babysitter's textbook.
Somehow people always bring that up because there's a line about it in my Wikipedia page. But okay, yeah.
Can we delve into that story? It brings to me like the story of Landau, when he also learned calculus at the age of 12.
I mean, if you really want to, I think, when I was younger than that, I had the idea that, okay, if you have like a series of numbers, you can take the cumulative sum and you can take the cumulative, you can take the pairwise differences, and these are somehow inverse operations, right, to each other, except that when you go backwards, then there's an ambiguity because there's a constant that you can add, right? So this was sort of like the discrete version of differentiation and integration, right? So I knew that, and I think, like, when you're trying to learn math and science, often the way that the progression works is that you start by rediscovering things that were, let's say 2,000 years old, or 400 years old, or something like that. But then if if it turns out that something was already well known, that's not a reason to give up, because next maybe you'll rediscover something that's only 50 years old. And then maybe you'll rediscover something that's only 10 years old, or that's only from last year, right? Until finally you discover something that was only discovered on the day that you discovered it. So this is what I always tell students, and so yeah, I started messing around with math, rediscovering things that were many hundreds of years old, and I did want to, I had a graphing calculator. I wanted to know what the buttons were, the sin, cos, tan, and so forth. And then when I saw, d over dx, and I saw this fancy looking S sign, I wanted to know what those were. And so I tried to learn what math I could. And then, I remember when I was 13 or so, like, I didn't know the formula for the length of a curve. But then, I just, nor did I know how to derive it. But then, I just sort of guessed the right formula from examples. And, again, that's like a 100 years old thing. It's kind of, a triviality to, people who really understand calculus. But I was very proud of it at the time.
Do you have any favorite, like, formula or theorem?
Oh my gosh. I mean, I can say like when I'm worried, if I'm too tired to concentrate, or recovering from surgery, or something like that, and I want to check whether I can still do math. Sometimes what I do is I try to just prove the Karp-Lipton theorem. The Karp-Lipton theorem is a beautiful little result in complexity theory that's about the power of what's called advice. So advice is sort of some information that could be chosen to maximally help an algorithm. But the catch is that you can only get a single advice string for each input length. Okay, so like it might be that for inputs of size 500, you get the advice string that's supposed to help you to solve any possible input of size 500. And the question is, if you were to get such advice from an all-knowing and trustworthy advisor, how much could that help you? And so the Karp-Lipton theorem is addressing, could that help you solve NP-complete problems in polynomial time? Example. Okay. And of course, we don't know whether there is a polynomial time algorithm for NP-complete problems. That's the P versus NP problem, one of the most famous unsolved problems in all of math and computer science. But now when you ask, could advice help? Now this is a new question, and so what the Karp-Lipton theorem says is that if NP-complete problems could be solved in polynomial time, even with the help of advice. Okay, so it says if NP is contained in this class called P/poly, which means polynomial time with the help of polynomial size advice strings, then this still would cause dramatic consequences to happen. It wouldn't necessarily mean that P equals NP, but it would mean that the polynomial hierarchy would collapse, which is a sort of higher up version of P equaling NP. Okay, so it says, if NP complete problems could be solved even with advice, then this would totally mess up the structure of complexity classes, even classes that have nothing to do with advice. Right. So, sometimes people parody complexity theory as like it contains a huge number of statements of the form like, if pigs could fly, then donkeys could whistle. You know, like if one wildly unlikely thing, happened, then so would another, right? But the point is, you want a sort of a standard yardstick of implausibility, right? And so like if we believe that this polynomial hierarchy is infinite, then which seems like a pretty reasonable assumption, then lots and lots of other things follow about lots of other topics. And the Karp-Lipton theorem is a nice example of that. And it just has a proof that is simple and beautiful enough that you can just remember it. You don't have to look it up each time. And so that's one of my favorites when, if someone asks me to write some math on a board or something, I might just write a proof of the Karp-Lipton theorem.
Maybe if we can get into like the foundations of the complexity theory.
Okay.
You already mentioned the P equal NP
Yeah.
problems, and maybe just to decode what it means for those who are not in this field.
Yeah. Okay. So P means polynomial time. So it's the class of all the problems that have an algorithm to solve them, running on a standard, deterministic digital computer like the one that we're having this conversation on right now. Um, and what polynomial time means is using a number of steps that increases only like the size of the input, the number of bits in the input raised to some fixed power. Okay. So the context here is that complexity theory is the field that tries to classify problems by the inherent resources needed to solve them, like how much time, how much memory, how much randomness, or quantum computing resources, or parallelism. Um, and so P and NP are two of the most basic classes that we study. We care, not just about like the raw number of steps, but typically about the scaling behavior. As you go to larger and larger inputs, at what rate is the number of steps that you need increasing? Okay, so what we like to see is, often the gold standard is linear scaling, right? Which would mean when your input is twice as large, then your algorithm takes twice as long, right? As would happen if you just, if the input is just a whole bunch of records, and you just need to go through and, scan them in a single pass. We also often encounter quadratic time. Okay, which would mean the number of steps grows like the input size squared. It would mean if you have twice as much data to process, then your algorithm will take 4 times as long. Okay, these are pretty reasonable scaling rates. What we don't like is exponential scaling. Okay, which would mean you need a number of steps that grows like 2 to the power of the number of input bits or something like that. Because then even if you had just 1,000 input bits, which is not very many, you would be talking about 2 to the 1,000 steps, right? Which is much, much more than, the number of atoms in the observable universe, or let's say, the number of nanoseconds that have elapsed since the Big Bang. Okay? Our sort of rough and ready, dividing line between what's efficiently solvable and what's not is what has polynomial scaling. So, right, which problems are solvable by some algorithm that that has scaling like like some power of the input size. The input length cubed or to the 4th power or whatever. And so the set of all such problems is strictly speaking decision problems with yes or no answers. That's what we call P. Okay, so you can think of this as sort of meaning the class of efficiently solvable problems. Now, it doesn't perfectly correspond to that because, for example, a problem that had an n to the million time algorithm would still be in P. No one thinks that that's efficient in practice. Okay. But what saves us is just that hardly ever shows up in practice, right? So P is our sort of rough and ready approximation to what problems are efficiently solvable. Okay, but now we come to NP, which stands for non-deterministic polynomial time. Okay, it doesn't stand for not polynomial. Okay, it's something much more subtle than that. Okay, NP you can think of as the class of problems where if someone tells you that the answer is yes, then they can prove that the answer is yes via a short proof that can be efficiently verified. Okay, so so now there's an asymmetry between yes and no, right? It's only the yes answers that need to be proven, okay? But the proofs have to be short, and there has to be meaning of polynomial size, and there has to be a polynomial time algorithm to check the proofs. Okay, so a good example here would be factoring numbers. Okay, so if I give you some huge composite number, and I ask you, let's say, does it have at least 3 prime factors, something like that. Okay, now that is that might be a very hard problem. Okay, we certainly don't know if it's in P or not, right? The best known classical algorithms for factoring, need a number of steps that grows exponentially, actually with the cube root of the number of digits that you're factoring. Okay, but on the other hand, if someone claims that the answer is yes, and then you don't believe them, then there's always something they could give you that would quickly convince you that the answer is yes. And the thing that they could give you is just the prime factorization of the number, right? if they have found it, then they just have to show that to you. Okay, it is what we call a proof or a witness. And then via a polynomial time algorithm, you can check that yes, these numbers really do multiply to your original number, and we even know ways to check that numbers are prime. Okay, if they're composite, they don't tell you what the prime factors are, but they do tell you if your number is prime or composite. Okay, so factoring is in NP. Okay, but there are lots of other examples. So the famous traveling salesman problem says, if like you have a bunch of cities and you ask, you give someone the distance between each city and each other one, and then you ask, let's say, is there a route that visits every city with at most 5,000 miles total? Right? Okay, that might be a very hard problem to
Is
solve.
that what Amazon is solving?
Not exactly, but they are solving, combinatorial optimization problems that are broadly kind of like that. Okay, so uh, uh, so if there are hundreds of cities, right, there might be an astronomical number of possibilities to try. We don't know if there's an efficient algorithm. Okay, but if you want to prove to someone that there is a tour with, at most 5,000 miles, you just have to show it to them, right? And then they can check. They can check that it really is a tour and that the distances add up to at most 5,000. Okay, lots and lots of problems have the same kind of character. Sudoku puzzles, jigsaw puzzles, the problem that many people may have encountered, where you have a bunch of suitcases of various dimensions, and you're trying to fit them into the trunk of your car, right? There might be a huge number of ways of rearranging them that you would have to try, but in the end, there's a simple test. Does the trunk close or not? Right. So NP, again, is the class of all the decision problems for which there is a polynomial time algorithm to verify a purported solution, to verify a witness that the answer is yes. Okay, and so now the P versus NP problem, which is maybe the greatest unsolved problem of theoretical computer science, arguably even of all of mathematics, is simply the question: are these two classes the same? Okay, it is easy to see that P is contained in NP. If you can solve a problem yourself, then you can also verify a solution. Okay, the interesting question is NP contained in P? So if you can verify a solution efficiently, then does that mean that you can also find a solution efficiently? Okay, so it certainly means that you can find a solution in at most an exponential amount of time, because there is always the brute force method of just trying every possible solution, one after the next after the next. Okay, but in some sense, what's being asked is there a general way to eliminate the need for brute force search? To just zero in on a correct answer whenever a correct solution exists and whenever it's efficiently verifiable, whenever it's easy to recognize once found. Okay, so this sort of captures a huge number of problems of practical interest, in optimization, in AI, in breaking cryptographic codes. Okay, and if P equaled NP, then like all of those problems would have efficient solutions. Okay, which that if that sounds wildly implausible, many of us share that feeling. I would say that the dominant conjecture is that P is not equal to NP. Okay, but the trouble is that proving that would require ruling out any algorithm that could ever be discovered.
Which is NP hard.
Well, no. It's a
Yeah.
fixed question,
Fixed
right?
question, okay.
It may just have a single fixed answer, but it just you could say the general problem of finding proofs, in fact, is an NP hard problem, right? We haven't even said what NP hard means yet. Okay, but uh, uh, um, the trouble is that there are lots and lots of problems, that may look like they don't have an efficient solution. Or they may look like brute force search is needed. Okay, so for example, solving a bunch of linear equations or solving a bunch of linear inequalities, even, right? It's not obvious, but there is a way to solve a system of linear inequalities that is polynomial time, that avoids the need for brute force search. Okay, that's called linear programming, right? Or if I give you a bunch of people and I tell you, who is willing to pair off with whom, who is willing to go on a date with whom, and now you need to set up the maximum number of people on dates, right? That sounds like it might be another one of these hard NP problems, but it isn't. Okay, it has a polynomial time solution that was discovered 60 years ago. Okay, so sometimes there really are clever ways to solve problems efficiently, even when it didn't look like it. Okay, another example that we already mentioned was determining whether a number is prime, right? Which was proven to be in P in 2002 in a breakthrough result. Okay, so now the question is, are there polynomial time algorithms for all the problems in NP? And I would certainly place a very large bet on no, but we don't yet have the tools to prove statements of that kind. Now, since
Does something really strange happen if P equals NP? Does something
yeah,
really strange happen? Like, does that then enable, I don't know, like
well,
faster than like travel or something?
no,
Like, is there
well,
something that really breaks if P is equal to
yeah.
NP?
So P equals NP would be a fact about math, right? It wouldn't be a fact about physics, in and of itself, right? So it doesn't change anything in the known laws of physics, right? But what it would mean is that first of all, essentially all of the encryption that we use, that is based on hard cryptographic problems, would then be broken. Okay, so for example, you could no longer have cryptocurrency, right? You could break all the steal all the Bitcoin, all the Ethereum, okay, and the only kinds of encryption that you could still have would be the kinds that are not based on hard computational problems at all, like for example, the one-time pad, or quantum cryptography would be another example. Okay, but pretty much all the forms of encryption that we currently use on the internet would be broken. Okay, but it would also mean, so I like to argue that P versus NP is maybe the most important unsolved math problem, and my argument for that is that if P equaled NP and the algorithm were fast in practice, we have to add that proviso, then you could actually, it would mean that you could ask your computer to solve all of the other great open math problems for you. Okay, so for example, we could just ask our computer, is there a proof of the Riemann hypothesis? Meaning a formal proof, a proof that is, from the axioms of set theory, that is like in a machine checkable format, like Cawk or Lean or some a formal verification language like that. Is there a proof of the Riemann hypothesis at most, let's say, 100 million symbols long? Okay? And if such a proof existed, then your computer could find it in time that is only modestly larger than the time needed to write the proof down. Okay, that's what it would really mean if there were a practical algorithm for all NP problems, right? You could, and this was a point that Gödel made in a letter that he wrote to John von Neumann 70 years ago when he said, he asked him what today we would immediately recognize as the P versus NP question. And he said, if there really were a fast algorithm, like let's say a linear or a quadratic one, it would have consequences of the greatest magnitude. It would mean that the mental effort of the mathematician could be completely replaced by machine, apart from the postulation of axioms. Okay, so this is sort of the stakes of the question, right? It would also have implications for AI. I mean, you may know that enormous amounts of money are being poured right now into the problem of building giant data centers to train neural networks to sort of solve one particular NP problem, which is given this neural net like GPT, O3 or whatever it is, and given this training data, find the setting of parameters in this neural net that minimizes the loss, that makes this neural net do the best at predicting this training data. Right? This is how modern AIs are created by spending massive amounts of computing power to train them, which means to find better and better solutions to this optimization problem of setting the parameters of the neural net. Okay, if P equaled NP, that would mean that you just had this super fast, essentially perfect solution to that problem.
Is there a connection between solving some of these like traveling salesman or like energy minimization problems and training a neural net? So for example, there's a lot of like either quantum or analog computer type work to
Yeah,
solve, I would call it like Ising problems or energy
yeah.
minimization problems. If you get very good at those, do you get very good at training neural nets by some kind of, proxy?
The answer is yes, you do. Okay, but in order to explain why, we don't really need to say anything about analog computing or anything like that, right? We just need to talk about NP completeness, okay, which was sort of the central discovery that really started modern theoretical computer science, in the early 1970s. Okay, so I explain what's the P versus NP problem, right? But now the surprising part was that it turns out that of all the NP problems that people want to solve, a huge fraction of them turn out to encode the entire difficulty of the class NP. Okay, meaning that these are problems that are sort of at least as hard as anything else in NP, right? If you could solve any one of these problems in polynomial time, then that would mean that P equals NP. Okay, that's what it means for a problem to be NP hard. That it sort of encode, that every problem in NP can be reduced to it. Okay, and if an NP hard problem is also itself in NP, then we call it NP complete. Okay, that's what these terms mean. Okay, and so what was discovered in 1972 or three was that actually most of the optimization problems that people really care about, including the traveling salesman problem, including bin packing, including a clique, which means if I give you, let's say, a graph of who is friends with whom on Facebook, find the largest set of people who are all friends with each other. Okay, a huge number of optimization problems like this that involve satisfying a whole bunch of different constraints actually turn out to be NP complete, which means that again, asking whether any one of these problems can be solved in polynomial time is the same as asking whether all of them can be, which is in turn the same as asking whether P equals NP. Okay, so there are what are called reductions that let us take one of these problems and encode it using another. Okay, so in particular, the traveling
But does
salesman.
that require a perfect solution? Does that require
Oh,
a perfect
okay,
solution
good.
to
So
the
okay, so
problems?
there's a whole theory of approximability and inapproximability that's developed since the 1990s. And so what we've learned from that theory is that for many NP-complete problems, even finding an approximate solution would already be NP-hard, right? So sometimes you can get very quantitative about it. So for example, there's one of the most famous NP-complete problems is called 3-set, right? It says like you have a bunch of yes or no, Boolean variables, and then you have a bunch of constraints that can involve 3 variables each. Okay, and your goal is to satisfy as many constraints as possible. A constraint might be like either this variable is true, or else this one is true, or else this one is false, something like that. Okay, and so it's pretty easy to satisfy a 7/8 fraction of the constraints, right? In fact, if you just set all the variables randomly, then you will satisfy like about a 7/8 fraction of constraints on average. Okay, but now a very deep theorem that was proved in 1997 says that if you had a polynomial time algorithm that could satisfy even slightly more than 7/8 of the constraints, like let's say 90% of them, and it could do that reliably, could do that for any instance, then that would mean P equal to NP. Okay. So sometimes we know these inapproximability results. In other cases, for other NP-complete problems, you actually can get like arbitrarily good approximations, but it's just the running time for any desired level of approximation, it will remain polynomial, but it will blow up as you want your approximation error to go to 0. Okay, so here, it can be a different story for different NP-complete problems. And this is still a huge topic that people work on, trying to understand. Okay, but when I say, that a problem is NP-hard, I just mean it is NP-hard, to find, whatever solution I asked for, whether that's an exact one or an approximate one, right? So again, if you could take any NP-hard problem and solve it in polynomial time, then that would mean that all problems in NP were solvable in polynomial time. That would include finding proofs of theorems. That would also include finding optimal sets of weights for training neural nets. Okay, these are all yeah.
Yeah, is there some intuitive explanation when you say that there is a set of NP-hard problems?
Yeah.
And then if we solve one of them in polynomial time, at least even partially, that would mean that we can solve other problems.
Yes.
Also in polynomial time. How to
Yeah. So
grasp a little bit better of the statement. I heard a lot about it, but
okay. Okay, good. So I mean, but by the way, okay. So what we're doing now is like a significant part of the undergraduate CS curriculum, right? Which is this is exactly the stuff that we teach our undergrads. Okay, the key trick is called reductions. Okay, so basically what you have to do is you say, suppose that I had just a magic box. We call it an oracle. Okay, but a magic box or a magical subroutine that solved any instance of the traveling salesman problem, instantly, right? And now, I don't want to solve the traveling salesman problem. I want to solve Sudoku, or I want to solve some other NP problem, right? So now what we need is a polynomial time algorithm that will take as input a Sudoku puzzle, so an instance of the Sudoku problem, as we put it, and that will translate it into a map for a traveling salesman, right? That has the property that if you found like an optimal route for the traveling salesman, then that would encode the solution to the Sudoku puzzle. Okay, so you need to find ways of encoding one problem via another
Is
problem.
it a trivial mapping, or
In
you
that
know
case,
that you can find?
it would not be trivial. Okay, but but one thing that helps, people starting in the 70s got really good at constructing these mappings. Okay, there is an art to it. Okay, uh, um, but one thing that helps is that if you want to prove that your problem is NP complete, so first of all, you have to show that it's in NP. That's usually easy to do. But then, you have to show that your problem is NP hard. Now, to show that your problem is NP hard, it's enough to take any other problem that is already known to be NP hard and reduce it to your problem, right? So you can search the literature for whichever problem seems the most similar to your problem, right? And then, if you can just embed that problem as a special case of yours, or show how it reduces to yours, then that's enough to show that your problem is NP hard also. So it's sort of like, NP hardness just sort of starts like from like a few problems where like you really, in order to prove the first problems were NP hard, you really had to just consider an arbitrary polynomial time, Turing machine that was doing verification, right? This is what Stephen Cook did in 1971. He showed that the three-sat problem actually was NP complete by just reducing from an arbitrary polynomial time verifier. Okay, but once you know that 3-sat is NP complete, then it was much easier to show the next 20 problems were NP complete because you just had to reduce 3-sat to them. Okay, and then once you had 20 examples of NP complete problems, then it's even easier to show that the next, however many hundreds of problems are NP complete. So that's sort of how it happened.
Yeah, I see. It's like a nice theorem, and probably two camps of people. Because if
Yeah,
if
so
there is a problem which could be p equals in p solved, then it's either on one side we can open the gate to solve one of the problems more efficiently. On the other side, let's say the encryption is going to collapse fully.
yeah, yes, yeah. So a priori, you might have imagined that there was just like this whole zoo of different disconnected hard problems, right? The surprise is that so many of the problems just organize themselves into these two universality classes, if you like. On the one hand, the problems in P, and on the other hand, these NP complete problems. And then there are a few in between, right? So there are a few problems in NP that we don't know to be in P, and we also don't believe are NP complete. Okay, and factoring is an example that seems to have that intermediate status. And actually, most of the problems that we use for present day cryptography are in that are believed to be in that no man's land in the middle.
Yeah. Speaking of like the prime number factorization, I think that
Yes.
was the hook for the quantum computing
Sure.
to
Yeah.
enter in the Shor's algorithm, which
Uh huh.
probably was the bright the bright at the end of the tunnel for quantum computing to solve.
Well, I would say it was I would say Shor's algorithm was the light at the beginning of the tunnel, right?
Beginning of
It
the
was
tunnel.
it was really the thing that started quantum computing as a whole research field when it was discovered 31 years ago. Most of my work for the last 25 years has been about the capabilities and limitations of quantum computers, and a quantum computer would, exploit quantum physics to, we hope, solve a slightly larger class of problems in polynomial time than just P. Okay, so we now get to exploit nature in a new way to do computation, and it gives us a new class of efficiently solvable problems, which is called BQP, which stands for bounded error quantum polynomial time. Okay, and BQP, which is the class of problems efficiently solvable by a quantum computer, contains P, right? So, at least anything you do with a classical computer, you can also do with a quantum computer. Uh, and of course, the very next question that people asked was, how does BQP relate to NP, right? And as far as we know today, even decades later, BQP and NP might be incomparable. Okay, so we don't know either to be contained in the other. Okay, so on the one hand, like we don't know how to solve NP complete problems in polynomial time, even using a quantum computer, right? Of course, we can't prove it's impossible because, we can't even prove that P is not equal to NP, all right? But that looks like, that would really require, totally new ideas. And on the other hand, we don't know if BQP is contained in NP. Okay, so there might be problems that quantum computers can solve where a classical computer could not even efficiently verify the answer, let alone finding it. Okay, so you get this P, and then there's BQP, and then there's NP. Sort of sticking up in two different directions. But now there's much more to say than that, and the big discovery that really started quantum computing as a research field, as opposed to like a crazy idea that a few people were thinking about, that really got computer scientists and mathematicians excited about it, was came in 1994, and that's when Peter Shor discovered that this factoring problem is in BQP. Okay, so he found that if you had a quantum computer, then there is a way to factor an n-digit number using a number of steps that grows only about like n squared, about quadratic with the size of the number. And by the way, that was recently improved to about n to the 3/2. Okay, so but in any case, it's polynomial time, and that's an exponential improvement over what we know how to do with a classical computer. And that is then evidence that BQP really is larger than P, right? It says either BQP has to be larger than P, or else the factoring problem has to be in P, right? Those are the only two possibilities. Okay. Now, it's very important to remember that factoring, is not known or believed to be NP complete, right? So, in order to design his quantum algorithm for factoring, Peter Shor had to exploit very, very special properties of factoring, that are shared by a few other problems in number theory and group theory, but that are not believed to be shared by any NP complete problem. Okay. And, ironically, those same properties from number theory are what make factoring so useful for cryptography, right? Like, why do we use factoring as the basis for modern encryption, right? Like, anytime we order something over the internet or we visit any website with HTTPS, like we are protecting our data, including our credit card numbers, by a cryptographic code whose security depends on the belief that factoring is hard, right? Or that a few, closely related problems in number theory are hard. Okay, so Shor, showed, of course, that if you could build a quantum computer, then that's no longer true. Then, you really could break most of the encryption that currently protects the internet, right? But you might wonder, like, isn't this a coincidence that the same problem that we use to protect modern encryption is the problem that quantum computers can solve? Okay, well, a part of it is explained by the number theoretic properties that make factoring so useful for encryption are the same ones that Shor exploits in his algorithm.
And yeah, at this point, Shor's algorithm, or like breaking RSA encryption, is this the lowest hanging fruit for the quantum computing, or there
What
are...
do you mean by the lowest hanging fruit?
Well,
Like,
to demonstrate that the quantum computing can, let's say, do useful
Yeah, well,
in a
okay.
way that outperform the classical.
Yeah. So okay. So I would say that I expect that well before we are able to break RSA encryption, like factor 2,000-digit numbers, we will first be able to use quantum computers to simulate quantum physics and chemistry in ways that are scientifically interesting, hopefully even commercially useful. So you could say, the original application of a quantum computer, that Richard Feynman and David Deutsch and others, had in mind when they first proposed the idea of a quantum computer 45 years ago, right? It was not factoring or anything like that. It was just simulating quantum mechanics itself. Okay. Right. So what inspired them was, the observation that the chemists and physicists, when they try to simulate quantum mechanics on conventional computers, they face this sort of exponentiality in the size of the calculation that they have to do. And this seems like it's for reasons that are very inherent to quantum mechanics, right? In quantum mechanics, we have this object called the wave function that captures everything that is knowable about a physical system, and the issue is that this wave function involves a number of parameters that grows exponentially with the number of particles. Okay, so if I have even just 1,000 particles, which is not very many, right? I could already have 2 to the 1,000 power parameters or more in my wave function, okay, which is more parameters than can be written down in the entire observable universe. Okay, so and this has been known about quantum mechanics, since Schrodinger wrote down his equation in 1926, right? So this is not a new observation, but chemists and physicists have known it for decades, mostly as a practical problem, right? That when you're trying to use your computer to calculate, let's say, what is the rate of this chemical reaction, or how is this material going to behave? Is it going to be an insulator or a conductor, or will it be a superconductor, and so forth? You have to do a calculation involving this whole wave function, and that can very quickly get infeasible, even with the largest supercomputers that are available on Earth right now. Okay, and so a lot of what chemists and physicists have done over the decades has been to invent all sorts of hacks and approximation methods for getting around that problem, right? But the great idea that Feynman and Deutsch had that led to the idea of a quantum computer was, well, if nature is giving us this computational lemon, then why don't we make lemonade out of it?
If you have a number of qubits, how do you connect that to, let's say, a chemistry or physics problem? Like, what's the connection between some whatever your qubits are, some atoms or whatever it might be? How does that connect to
Yeah.
like an actual
So
problem?
so okay. So just like we were talking about before with NP completeness, there is a mapping that you need to do from one system to another, right? And often these mappings will be non-trivial, right? So for example, but Feynman was already talking about this when he gave his now famous lecture that introduced the idea of quantum computing in 1981. I think. Okay, and he was talking about how would you take a system of bosons or fermions, like the types of particles that arise in nature, and map that onto a system of well, what we would now call qubits. Okay, the word qubit hadn't been coined yet. Okay, but you could say, and so the details of how that works will often be somewhat complicated. But that was also true with classical computing, right? Like if you want to simulate some fluid flow, or some galaxy, rotation with your classical computer, right? You have to take all the physics of your system, all the fields and the interactions, that there are, and map it onto, this abstract system of bits, right? But this is what, you know, This is what we do in computing, right? We figure out how to do those things, and there's a bunch of tricks that recur. Like one trick is to divide up time. Instead of treating time as a continuum, you discretize time, right? You treat it as just a bunch of discrete little steps, and then within each step, you break down everything that's happening within that little tiny sliver of time as a sum of local interactions, right? So you use the fact that the laws of physics are local. They consist of you know, like interactions between pairs of particles or things like that. And so then you just sum up, for each pair of particles or for each interaction, you calculate the effect that has over that tiny little time step, and you apply it, and then you move on to the next time step, right? I mean, that's true in classical physics simulation, and those same ideas are also used in using a quantum computer to simulate a quantum system. Right. So, I mean, there's much more to say about it than that, but I hope that gives you some flavor.
Yeah, from my opinion, currently I see a strong trend towards discrete, uh, solving like discrete quantum circuits instead of what you mentioned, more like simulations. So where the main players go towards like a quantum fault tolerancy.
Yeah.
So what's your take on this trend?
Yeah. Okay. So we need to distinguish two things, right? There's the discreteness or not of the computer, and then there's the discreteness of the system that we're trying to simulate, right? So we can use a discrete quantum computer, which means a quantum computer made out of qubits, even to simulate a continuous quantum system, right? If we take care to discretize things in the appropriate way, right? And that is something that people are already doing. I expect that they'll continue to do that, and that's directly analogous to what we do when we simulate classical physics, on classical computers, right? But in the old days, if you go back to the 40s, the 50s, the 60s, right? People had the idea that, well, since if nature is analog, then we should build analog computers to simulate it with, right? And they did. They built all sorts of clever devices, that could solve differential equations by mapping them onto some analog system. Okay, but then that idea basically lost out, right? It lost to the digital approach. Okay, and there was a very, very deep reason for that. Okay, it's because when things are digital, then you have some degree of robustness built in, right? You know that each bit is either a zero or it's a one, right? And if an error happens, if a zero flips to a one or a one flips to a zero, that's a discrete thing that's happened, and you can detect when it's happened, and you can fix it, right? When the basic elements of your computer are analog, then the danger is that they're just going to drift over time from the values that they're supposed to have. And that drift can just sort of amplify itself chaotically over time until your entire computation gets destroyed before too long. Right. So that's sort of the reason why, even for the task of simulating analog systems, digital computers won, right? Completely decisively, right? And I expect the same to ultimately be true with quantum computers, right? There are analog quantum simulators that you can use, and in the near term, that like you may get wins that way. That may be a thing that people do, but the eventual goal is to have the quantum version of just a reliable digital computer, right? Where you have qubits, they are error corrected, so we know exactly what operation we're doing to any qubit or any pair of qubits. And then, we just program in whatever sequence of operations we want in order to simulate, whatever physical system we want or run whatever quantum algorithm we want to factor a number or whatever. So that's the eventual goal. We would call it a universal fault-tolerant quantum computer. And we're not there yet, but we are enormously closer than we were, well, let's say, when I entered this field 25 years ago.
I see. Maybe speaking of usefulness of quantum computer, I've seen recently in the news there was announcement about that the work on random number generators.
Yeah,
So maybe if you could speak
sure,
about
sure.
if we can leverage quantum computers for this kind of tasks.
Yeah. So okay. So some context here is you could ask, like, what is a quantum computer good for, right? And I've given you two answers that I think are very dramatic, but and true, but also very specialized, right? The first answer was simulating quantum physics and chemistry themselves. Okay, and I think if and when we get this fault tolerant scalable programmable quantum computer, that's actually the biggest application that we know, to be honest, right? Why? Because that could be helpful to the battery industry, the photovoltaics industry, the to biochemistry, drug design, making fertilizer, sort of any kind of problem where people are dealing with, many body quantum mechanics, right? Which is a lot of chemistry and biochem and material science. So I really do think that quantum computers could have an economic impact there, right? Now, the second application that we talked about was breaking most of the cryptography that currently protects the internet, specifically the kind that's based on number theory problems like RSA and Diffie-Hellman. That it's hard to put forward as a positive application for the world. It's a positive application for whichever intelligence agency or criminal syndicate gets it first, as long as, especially if other people don't know that they have it and, so are not upgrading to, newer forms of cryptography that will hopefully be quantum resistant. Okay, but so now for 30 years, we've been trying to figure out what else is a quantum computer good for, besides those two areas, quantum simulation and code breaking. And, we have a few answers to that. There's another very important quantum algorithm called Grover's algorithm, okay, which has much broader application than Shor's algorithm does. It can be used for NP-complete problems. Okay, it can be used for basically any problem that involves searching through a huge list of possibilities. Okay, but the trade-off is it does not give you an exponential speedup. Right, the speedup that it gives you is merely by a square root. Okay, it's a quadratic speedup. So you can search through a list of n possible solutions in about the square root of n steps. Okay, so that's something, right? That's it's something that just certainly would not have been possible with a classical computer. Okay, but we also have a proof that for this abstract search problem, Grover's algorithm is the best that even a quantum computer can do. Okay, so this square root of n is in some sense optimal, without further exploiting the structure of the problem being solved. And so now the issue is it's going to be a very long time probably before Grover's algorithm becomes a win in practice. Okay, and the reason is that in order to run an error-corrected quantum computation, like we were talking about, you need these very clever quantum versions of error-correcting codes. So we haven't talked about that yet, but they're going to induce a large overhead. Okay, so optimistically, that overhead might be by a factor of 1,000,000, let's say.
And also rivaling the Moore's law from the
Well, yeah, well,
semiconductors
of
chips.
course, you have to beat, the best that can be done with a classical computer. I mean, that is always the hard part in quantum computing research. right? It's not enough to just say my quantum algorithm can do such and such, because, if you're scientifically honest, then the next question is, well, could a classical computer also have done that, just as well, right? And unfortunately, we now, see this unbelievable amounts of hype, right? Because, these startup companies in this space learn that they can raise lots of money and get lots of people excited by just saying, we can use a quantum computer to do financial portfolio planning and neural nets and, all these other things that you're excited about. And they don't even notice the question of, is there any advantage over a classical computer? And they trust other people to not notice or care about that question, right? Which to, those of us who work in this field is the only question, worth caring about, right? So yeah, you have to beat classical, and classical algorithms can be incredibly clever. And as you said, classical hardware keeps improving because of Moore's law. Okay? So with Grover's algorithm, you get the square root speed up, but then there's also this enormous overhead from running error correction. And so when n, your number of potential solutions, becomes sufficiently enormous, then Grover's algorithm should become a win. Okay, but that might have to be when n is larger than 1,000,000 times the square root of n, right? Which only happens once n is in the trillions. Okay, so that's Grover, and so we've been trying to expand the list of what a quantum computer is good for. There have been many attempts. There are quantum algorithms that are heuristic, which means that we don't really know how well they're going to perform or whether they're going to outperform the best classical algorithms, and we may not know until we can really test them out on large quantum computers, right? So, and then there are quantum algorithms that for machine learning problems that seem to give an exponential speed up, but the speed up is not really end to end. It's like for transforming one class of quantum states into a different class of quantum states. But, what we care about at the end of the day is transforming a classical input into a classical output, right? And for that full end-to-end problem, it's often much, much less clear whether the exponential quantum speedup survives. And sometimes, it's been claimed, well, that, here's an apparent exponential quantum speedup, but then later the algorithm gets dequantized. It gets a classical algorithm later gets discovered that can get similar performance to what the quantum algorithm had. So a then 18-year-old undergrad who was working with me in 2018 by the name of Ewin Tan had a major achievement along those lines when she dequantized one of the main quantum algorithms that was known for machine learning problems. Okay, so what can we do to discover new quantum algorithms, right? And so what a lot of people have done is say, well, here's what we really want to solve. We really want to train neural nets faster, or improve oil and gas exploration, or whatever it is. So let's just try to force fit quantum computing into that. I would say people have not had that much success in doing that. It's like, again and again, the answer is, well, there's Grover's algorithm. There's a bunch of other stuff that looks kind of like Grover's algorithm, but it all just gives you these modest advantages. And then if you want exponential advantages, then they only apply under some very, very special conditions that, who knows where those conditions will ever hold in practice. Right? Like that, like again and again, that seems like the story. Now, the approach that I would advocate, and where I think that there's been a lot more success, is to just start from what is a quantum computer good at. So, where do we see exponential quantum speedups at all, even for just completely useless, benchmark problems, right? So just forget about usefulness in the beginning, okay? And then once you understand that, then you can say, okay, now that we have this quantum speed up, what might it be good for? And so this protocol you mentioned for which I proposed 7 years ago for generating cryptographically certified random bits using a quantum computer, that was a very good example of this approach. Right. So so the context here was that so I've been very involved since 2009 or 2010 or so in designing what we now call quantum supremacy experiments. Right, and these are experiments that just try to do some task using current quantum compute, or using near term, so non-error corrected, non scalable quantum computers, but do some task much faster than we know how to do it classically. And notice that I did not say a useful task. Right? It doesn't have to be useful. Right? It can just be any well-defined benchmark. But we want to see the quantum computer win, and we want to do it using the sorts of devices that we can build now. Right? So not needing a full error correction. So I had one of the earliest proposals for how to do that. I and my student, Alex Arkhipov, and this was called boson sampling. And our basic idea was, instead of, sort of forcing your quantum computer to solve some really, really special problem like factoring a number, let's just look at what quantum systems do naturally, right? And the system that we, it's kind of like if you wanted to prove that a dolphin was intelligent, right? You could train it to solve arithmetic problems. Maybe you can with heroic effort, but you could also just watch it swimming around in the ocean, interacting with other dolphins, and you'll probably see it you'll probably see it demonstrate much greater intelligence that way, right? So so what we were thinking about was just a network of beam splitters, which are like these very simple optical components, right? And what happens if I send a collection of identical single photons into a network of beam splitters? Right? And so, the photons move around because this is quantum mechanics. They have a wave function, right? So they evolve in a superposition state, where there's some amplitude for every possibility of where all of my photons could go. Okay? And then at the end, I can measure them. I can, at each output port where a photon could emerge, I can make a measurement to say how many photons are there. And so, and that's all you can really do in our setup. Okay, so a boson sampler is not a universal quantum computer. And for that matter, we don't even think it's a universal classical computer. Right. But what we said is let's look at if you wanted to take this setup of photons, traveling around through beam splitters and simulate it using a classical computer, then how hard would that be? Okay. And we gave evidence that to simulate this setup on a classical computer would take time that grows exponentially with the number of photons. And basically the way that we did this was, instead of trying to get a particular answer out of our setup, we said, well, let's just look at the sampling task. So let's just say that, let's just define the problem to be sample from the probability distribution over photon locations that this beam splitter network would sample from, right? So now, like, it is not interesting that this beam splitter network can solve that problem, right? It is obvious, right? It solves that problem by definition, right? The interesting part is, how hard is it for a classical computer to sample from that same distribution? And here,
What's the reason that a quantum computer, like, what's the fundamental kind of like speed of the quantum computer, or quantum mechanics in general, contains that would speed that problem up? Is it like the matrix multiplications behind quantum operations, or what's the speed
that's
up?
that's one way of thinking about it. But you could say maybe the most fundamental thing is just that the wave function is exponentially large, right? So in order to keep track of what n particles are doing, I need a number of parameters that grows exponentially with n, right? I need this wave function. Okay, I need to write down this complex number called an amplitude for every possible configuration of all of the particles together. This is the fundamental way that quantum mechanics is different. And this is the thing that a quantum computer is trying to exploit. Uh, now, that is such a dramatic change that, when people heard about this, like, let's say, shortly after Shor's algorithm was discovered, this way of talking about it got into the popular press that, that sounded really good. Everyone liked it, right? They said, well, quantum computer, it must be exponentially faster because it could just try every possible solution in parallel, right? It just tries them all, at once in superposition, right? And, that sounded great. Unfortunately, that's not really true, right? That's that's sort of gesturing towards something true, but it's much more subtle than that. Okay? Now, the main difficulty is that it's true that with a quantum computer, because these wave functions are these exponentially large objects, you can create a superposition over all the different answers to your problem, even if there are exponentially many of them. Okay, that's even an easy thing to do with a quantum computer. Uh, but in order for a computer to be useful, at some point you have to look at it, you have to measure it, you have to get an output. Okay, and if you just measure it in equal superposition over all the answers, not having done anything else, the rules of quantum mechanics are unequivocal about what you'll see. And, all you'll see will be a completely random answer. Okay. And well, if you just wanted a random answer, then you could have just flipped a coin a bunch of times, right? You could have saved the billions of dollars to, build this quantum computer. So the only hope of getting an advantage from a quantum computer is to exploit the way that these amplitudes, right, which are the components of these wave functions, being complex numbers, are different from probabilities. Okay, so the fundamental numbers in quantum mechanics are called amplitudes. Right. So basically, the thing that quantum mechanics says is that to every possible, configuration of your particles, you need to assign an amplitude. Right. That's what a wave function is. Uh, and what are amplitudes? Okay, well, they're very related to probability, right? To how likely is it that you will see the particles in this configuration if you look? Okay, but they're not probabilities. Okay, and an easy way to see how they're different is that amplitudes can be negative numbers. Okay, they can be positive numbers or negative, or in fact, they can even be complex numbers, involving the square root of -1. Okay, so what quantum mechanics says, you have to assign an amplitude to every possible configuration of your system, and it's these amplitudes that evolve over time as your system changes via matrix multiplication, as you said. That's where matrix multiplication enters the story. Okay, but now the hope of getting an advantage from a quantum computer all rests on exploiting how amplitudes are different from probabilities. Okay, so and the main way that they're different is that they can, as we say, interfere with each other. Okay, so if I want to know, like, what is the final amplitude for my particles to get to such and such configuration, right? There may have been many different ways that the particles could have gotten to that configuration. Okay, and each possible path that they could have taken makes some contribution to the total amplitude, right? If I want to know the total amplitude, I have to sum together all those different contributions. This is another way of thinking about quantum mechanics, right? Or about or for that matter, about matrix vector multiplication, right? It's, at some level, all that's going on is I'm multiplying matrices, okay? But that leads to a whole bunch of contributions that need to be summed up.
So
Okay?
would it be fair to say, based on what you just said, that quantum computing particularly useful if we need to store large amounts of information, so that this
No.
exponentiation into
Yeah.
the number of qubits you can encode
Yeah. So I mean
a
that
number of
that
information.
that is that is a thing that you might hope. But again, the difficulty is that when we make a measurement, we don't see all these amplitudes, right? When we make a measurement, when we look at our system, we collapse its state, okay? And then we just get a random result. Okay, so even if you had, stored all this information into a gigantic superposition, you will not be able to reliably read it out by measuring the system. Okay, that's what I'm trying to explain. Okay, so the only hope of getting an advantage with a quantum computer is to exploit, the way that amplitudes work differently. Okay, and so with every algorithm for a quantum computer, right, you are trying to choreograph a pattern of interference so that for each wrong answer, each answer that you don't want, you have some contributions to its amplitude that are positive and others that are negative. So they cancel each other out. Okay. And so that you get a total amplitude that is zero or close to zero. Whereas for the right answer, the answer that you want to see, you want all the different contributions to its amplitude to be reinforcing each other. If you can arrange that, then when you measure, you will see the right answer with a large probability. The tricky part is that you need to do this even though you yourself don't know in advance which answer is the right one. Right? If you already knew, what would be the point? Right? And you have to do all of this faster than the best classical algorithm could have found the right answer. Okay, this is what Shor showed how to do for the problem of factoring numbers, right? By exploiting very, very special properties of the factoring problem. Okay, it is not just a generic exponential speedup for anything. And the reason why it isn't is that when you measure, you just get this tiny little sample. Okay. Now, I can go back to the thing you asked me before about sampling problems. So what Shor had to do was sort of concentrate all the amplitude onto this sort of tiny of outputs that reveal information about the prime factors of your number, right? And that's sort of a very, very finely tuned thing to ask for. We only know how to do that using a fully error-corrected quantum computer, which of course we don't have yet. Okay, so what Arkhipov and I suggested with boson sampling in our paper 15 years ago was just take a bunch of photons or other bosonic particles, let them evolve, let them move around through this network of beam splitters, let them form whatever complicated quantum superposition state they thereby form with some exponential number of different amplitudes, and then just measure. And then you just see a sample. And then you can do it again. And you'll see another sample, right? So you're just sampling from this very, very messy probability distribution. Probably, in the whole lifetime of the experiment, you will never see the same output twice, right? Because there's just such a vast number of possible outputs. So you could say, well, then how could this possibly be interesting? Well, the key is for some of the outputs, there has been a little bit more destructive interference. And for some outputs, there's been a little bit more constructive interference, right? So the amplitudes are not all the same, okay? The distribution is not uniform, right? Some outputs are going to be likelier than others, twice as likely, 3 times as likely, things like that. And that means that if you collect enough different outputs and then you do statistics on them, which, may require a very hard calculation with a classical computer, but let's assume that you're willing to spend the time to do that. Okay, then you can actually see that this quantum computer, really was working as intended, right? It was producing samples according to this crazy distribution where plausibly a classical computer would not have been able to sample from that same distribution in any comparable amount of time. So this was the basic idea of these quantum supremacy experiments. Okay, so again, we proposed this and the paper came out in 2011. Other people had similar ideas around the same time. And then in 2015, Google said, we want to build a system with 50 superconducting qubits, and we want to do this type of experiment, this quantum supremacy demonstration based on sampling. Okay, so we worked with them to help design that experiment. So what they ended up doing was not boson sampling, but it was something sort of inspired by boson sampling that was more tuned to their hardware, to what they were building. And they announced the results of that experiment in 2019. Okay, and they said, with 53 qubits, we have sampled from this distribution that we think that a supercomputer would have taken 10,000 years to sample from. Right? And so then that number got all over the press, and then that was a little hasty, unfortunately, because just a few weeks later, IBM said, well, actually, we can sample from that same distribution much faster. Maybe in just a few days or a few weeks. So the quantum computer still had some advantage, but it wasn't, it wasn't
was expected.
10,000 years, right? And then people whittled away at the quantum advantage, because this is this is what's supposed to happen. This is how this field works, right? Classical computing gets to fight back. Okay, but what also happened was that the quantum hardware has continued to improve from 2019 until today. And so just this past December, Google announced a new quantum supremacy experiment with, I think it was 103 qubits, and like 40 layers of operations on them. And here they said, even using the best classical algorithms that have been designed, in the years since 2019, to try to simulate their earlier experiments, still it would take about 10 to the 25 years to simulate, to sample from this distribution.
So it was not disproved yet.
That's right. It is still standing. Okay, but there's a big caveat right now, which is that even to just directly prove that Google's quantum computer is working correctly, that would also take 10 to the 25 years on a supercomputer, as far as we know. Okay, so, they do like plausible extrapolations where it seems like their device is working correctly, but to directly verify the outputs with a classical computer, that seems just as hard as spoofing them with a classical computer. Okay, so I view, maybe the biggest theoretical challenge in this field right now to be, can we design a quantum supremacy experiment that is, first of all, beats classical computing? That's the obvious thing. Second of all, is doable on a current device. Okay. Third of all, has an answer that can be quickly verified with a classical computer. I would say the current situation is that we know how to achieve any two of those three conditions. So, like, for example, Shor's algorithm should eventually beat classical computers and in a way where we can quickly verify the answer, but we can't implement it with the current devices.
So at the moment, we cannot verify what the Willow chip produces.
We can verify all the way up to the limits of what classical computers can do, right? So we can go up to 50 or 60 qubits where you can still verify if you will use the biggest supercomputers on the planet and have them spend weeks or months on it. And people have actually done this now, right? And you see that the quantum computer is getting the right answer, and it's getting it way, way faster then we would have known how to get it with the supercomputer, right? So this you can do, but you can't go completely beyond the realm where the supercomputer could simulate it, because if you did, then you're also completely beyond the realm where the classical computer can check the answer.
Yeah, it
So
actually resembles the omnipotence paradox. Like, can God create a rock? So he cannot
right,
lift it, and then can Google make a quantum computer or just a
but not
computer
even
and
it.
cannot verify?
Yeah, right. Except here, Shor's algorithm should solve the problem, right? And the reason we think that this is ultimately a solvable problem is that we believe P is different from NP. There are problems like factoring where, that may be very hard for a classical computer to solve, but where it's still easy for a classical computer to recognize a right answer. Okay. And some of those problems, like factoring, are in BQP. So eventually we expect to solve this, but it seems that the currently known ways of doing it require a fault tolerant or an error corrected quantum computer. Okay, now I can talk about the generating certified randomness. So in 2018, as Google was preparing to do this quantum supremacy experiment based on sampling, I was thinking about, like what it could be good for. I had a conversation with a colleague where he mentioned this idea of certified randomness, which means, generating bits that are not only that are random, right? And let's be clear, if you just want random bits, okay, that's easy to do. Right. There's many, many ways of getting random bits. There are even websites you can visit that will generate random bits on demand, okay, using radioactive materials, for example. Some of them use quantum mechanics, or I think there's a company, Cloudflare, that has a bunch of cameras pointed at lava lamps, okay, and it's on a shelf somewhere. Okay, and you just use the patterns in these lava lamps to get a source of randomness. So there's many, many plausible ways of getting random bits. Okay, but now here's a harder challenge. How do you prove to a skeptic over the internet that your bits were really random, right? You may say that you generated your random bits using using radioactive material, with a Geiger counter, or using a lava lamp, or from the granules on the surface of the sun or whatever. But if they don't have the kind of hardware that you have, or they don't have access to your hardware, why should they believe you, right? Like if you're going to be using these for something cryptographic, like why shouldn't they suspect that maybe you just secretly replace these numbers with pseudo-random numbers that you know how to predict, even if they don't. Hey, and there's even real precedent for worrying about this. The NIST in the U.S. agency had a pseudo-random number generation standard that was called dual EC DBRG, I think. And what we learned from Snowden a little more than a decade ago, that the NIST standard, or one of them, had actually been backdoored by the NSA. So the NSA knew how to predict these, supposedly pseudo-random bits that were not supposed to be predictable by anyone. So, how do you show that your random bits have not been secretly backdoored? Hey, this is the challenge. And, it might even sound like it's just unsolvable in principle, because, there could always be a pattern that just, you can only ever, prove that there is a pattern. How could you ever prove that there isn't one? Right. But what I realized in this conversation with my colleague was that you could take these sampling-based quantum supremacy experiments that Google was then planning to do, and you could almost immediately repurpose them to get a way of generating cryptographically certified randomness. So here's how it would work. Okay, so you would have like a skeptic that generates a circuit to send to Google, let's say, and in order to generate this circuit, the skeptic will already need a little bit of randomness, okay, but only a small amount, okay, what we call a seed, right? So they need a very small amount of seed randomness in order to generate this challenge circuit, okay, and then what we're going to get out at the end is going to be a much larger amount of randomness. And so now Google receives this challenge circuit, and now what they need to do is run that circuit on their quantum computer. A circuit just means like the sequence of operations that the quantum computer is supposed to apply.
Sounds like randomness amplification.
Yeah. That exactly. So Google has to initialize their qubits, let's say, to the all zero state, then apply this given sequence of operations, and then measure all of the qubits, right? Now, each time they do that, they're going to get some sample from a probability distribution. If there are n qubits, then each time they measure, they're going to see an n-bit string. Okay, and so now they're asked to just send those strings back to the skeptic and send them quickly. Like, we'll give them a time limit. Like they only have 2 seconds to do this, or something like that. And now the skeptic, can then generate a new challenge, send it to Google, get back new responses, and so forth. Okay. And then at its leisure, the skeptic can verify that Google really was sampling from the correct distributions. Now, as we talked about before, this is the hard part. This is the part where you really need like a classical supercomputer, right? Or like a very big computer. Okay. And it's a huge challenge to figure out how to make the verification efficient. But for now, we'll just assume that we're doing these sampling runs with a 50 or 60 qubit device. So it's hard to simulate with a classical computer, but it's not impossible. You can still do it with like a really big supercomputer, and maybe the verifier occasionally does that, or even just threatens that it might do it in order to keep the quantum computing, in order to keep Google honest. Okay, and now here's the key realization. Okay, that once you verified that the hard distribution is being sampled from, or like that, like you apply the statistical test to the outputs and the test passes, then under some very plausible cryptographic assumptions, that hard distribution could only be sampled from, even by a quantum computer, by sampling the answer randomly. Okay, so in other words, even a quantum computer should not have been able to quickly pass this challenge in a way that was secretly deterministic. Okay, so in this way, you get a sort of guarantee that if the problems that we expect to be hard really are hard, and if the quantum computer solved the sampling task quickly, then it had to have done so by actually sampling random bits. Like the Google could not have secretly subbed in a classical pseudo-random generator, because if they had done that, then this test would have failed.
So is this quantum circuit sampling, is it an NP-hard problem? Would it be the...
No, it's not. No. These are not. So we don't expect that anything that a quantum computer can do is solving an NP-hard problem. As I said, we NP is not known or believed to be contained in BQP. So this is a different kind of hardness, right? Now, it is kind of a subtle story, because like if you go back to the beginning of these quantum supremacy experiments, like the paper that Arkhipov and I published in 2011, right? What we the way that we argued that this distribution should be hard for a classical computer to sample, it involved a type of hardness that is even beyond NP hardness. Okay, something called sharp P hardness. Okay, so sharp P is sort of the class of all the combinatorial counting problems. Okay, so like where I would give you some, let's say I give you the distances for the traveling salesman, and I don't just ask you, is there a tour that's less than 5,000 miles? I ask, how many such tours are there? Right, and and these are believed to be potentially even harder than NP complete. Like even if P equal to NP, we still wouldn't know how to solve these counting problems in polynomial time. Those might still be exponential for all we know. Okay. But certainly they're at least as hard. Okay, because if you just decide whether the count is 0 or non-zero, then that's the same as deciding whether there is a solution or there isn't one. Right, which is the NP hard problem. Okay, so short P we think is even above NP, and so the observation that sort of got us started on this whole journey was that if you look at the amplitude for a bunch of bosonic particles like photons to get from an initial configuration to a final configuration, where these particles haven't interacted with each other, then that amplitude is a function called the permanent. So it can be represented as a certain function of an n by n matrix if there are n photons, which is called the permanent function. And I don't know if you've ever seen the permanent, but you can look it up on Wikipedia. Its definition, it looks almost exactly like the determinant, except that in a place where the determinant has like a minus signs in it, the permanent has no minus signs. So it's just like a sum over all permutations of the product of the entries of the matrix along that permutation. Okay, that's what the permanent is. And now one of the big discoveries in theoretical computer science in the late 1970s was that this permanent function is sharp P hard, hey, which again is even beyond NP hard. So that this was proved by Leslie Valiant. He won the Turing Award, partly for this. Okay, but so it was once again it was a reduction, right? He showed how to take any combinatorial counting problem and encode it as calculating the permanent of some matrix, even just a matrix of zeros and ones. Okay, and so then what we noticed was, first of all, that bosonic amplitudes are permanents, right? And this is a thing that physicists have known for a long time, right? And second of all, that the permanent is sharp P hard, right? And when you put those two things together, it becomes almost irresistible to ask, wow, does this mean that quantum mechanics can solve a sharp P hard problem, right? And that sounds too good to be true, right? And I think other people had that thought before us, and and they came to the same realization that we did, that it's yeah, so it sort of is too good to be true, right? The trouble is that once again in quantum mechanics you don't get to directly see the amplitudes, right? So when you make a measurement, like the amplitudes determine the probabilities that you see the various possible outcomes, but then what you see is just, there's this many photons here, there's that many photons there, right? You don't actually see what was the amplitude for the photons to end up in that state. If you did, then you would have solved a sharp P complete problem, but you don't get to see that amplitude. So now the change that we made when we did boson sampling was just to say, well, let's, again, just like watching the dolphin in its natural habitat, let's just look at what the system does do. Okay, and what does it do? Well, it samples from a probability distribution in which the probabilities are given by permanence, or rather the amplitudes are given by permanence, but then probabilities are the squared absolute values of amplitudes in quantum mechanics. So we get to, in effect, sample a random matrix, but in such a way that matrices with large permanence are more likely to be sampled than matrices with small permanence. Okay, so this is the thing that quantum mechanics does let you do. And so we said, well, let's study how hard is that, right? And what we were able to do was to use the sharp P hardness of the permanent, of calculating the permanent of a given matrix in order to show that boson sampling, which means like sampling a random matrix in a way that's biased toward larger permanence, that while that problem is not itself sharp P hard, it is still plausibly very hard, right? Like if that problem were efficiently solvable, then because the permanent is sharp P hard, this would cause weird things to happen to classical complexity theory. And actually the thing that would happen, we to go all the way back to the beginning of this conversation when we talked about the Karp-Lipton theorem, right? And I said like, if NP-complete problems were efficiently solvable using advice, then the polynomial hierarchy would collapse, right? It would actually collapse to what's called the second level. So Arkhipov and I showed that if you had an efficient classical algorithm, a polynomial time classical algorithm that samples from the same distribution that an ideal boson sampling experiment samples from, then the polynomial hierarchy would collapse to the third level. Okay, and we proved that by using the sharp P hardness of the permanent. Okay, so it's like you get this nature is not going to give you a sharp P hard, the solution to a sharp P hard problem. She is more subtle than that, right? But she gives you the shadow of sharp P hardness, as it were. Now all of this is assuming that you have a perfect experiment with no noise, okay, which of course is not a realistic assumption. Okay, and so then, what most of our paper was about was, okay, suppose that there's noise in the experiment, and then you have to make a stronger assumption. We think that the polynomial hierarchy would still collapse, but now we need to conjecture something else in classical complexity theory that is still not known to this day. That basically and actually here this circles back to another thing you were asking about before about approximation problem, right? So like some NP hard problems are still NP hard to approximate, others are not, right? So now the question that we ask in the boson sampling paper that we don't know the answer to is if I give you a random matrix, so like a matrix of independent Gaussian entries, and I just ask you to approximate the permanent, is that a sharp P hard problem? Okay, so we know that to exactly compute the permanent of a random matrix is a sharp P hard problem. And we also know that to approximate the permanent of a worst case matrix is a sharp P hard problem. Okay, but now we ask, what if you have the approximation and the random matrix in the same problem? Right? Is that still sharp P hard? If it is, then we showed a classical computer cannot even approximately simulate a boson sampling experiment unless the polynomial hierarchy collapses. Good. And now I told you what we did 15 years ago.
So it sounds like you're very optimistic about like the future of quantum. So let's say the community like all set towards the quantum fault tolerance.
Yes.
My question is like, what would happen after quantum computing? Do you see?
Okay, so first of all, when you say optimistic, it depends on what about, right? So I am yes, I am optimistic that if people want this enough, they can build fault-tolerant quantum computers, right? And they should work like the theory says. I mean, just like in the days of Charles Babbage, however far away we were, from it technologically, I think, like it was reasonable to be optimistic that eventually we should be able to build a reliable classical computer, right? And today, I think like in the 1990s, we were maybe still in the Charles Babbage era of quantum computing. But today we are well past that, right? Today we have these programmable devices with 50 qubits or 100 qubits. Last year, Google actually demonstrated an error-corrected qubit, that gets better with increasing size. Okay, so they've finally crossed that threshold after 30 years of talking about it. Okay, so I would say that now we're in, we're not yet in the transistor era of quantum computing, but we're in maybe the 1940s, or we're in the vacuum tube era, or the electromechanical relay era of quantum computing. Okay, so yes, you have Google, IBM, Microsoft, Amazon, a whole bunch of venture-backed startups, all spending tons of money to try to make this real. You can argue about, is that wise or is it unwise? But in any case, they are doing it, right? And so, I think, it is reasonable to be optimistic that, yes, eventually we can get this. Now, what is it going to be good for? That part, unfortunately, has been massively, unbelievably overinflated in the popular press. Right. I've tried to give you a true sense of what it will be good for. It will be good for quantum simulation. It will be good for breaking public key cryptography. It, should provide some modest benefits from other things. For example, via Grover speedups. It can do this, certified randomness, protocols like that. And maybe there are other applications that are yet to be discovered. That's entirely plausible. Okay, but it is not this magical machine that just speeds up everything, right? And I don't expect that most of us would ever need a quantum computer. And one reason for that is simply that we already have the cloud, right? If you ever needed, to solve those problems that a quantum computer helps with, then you can just access it over the internet.
I have a question related to that,
Yeah.
which is like maybe there's a different kind of quantum object that it makes sense for people to own personally, which is I think I worked for a while on reducing the energy consumption of Bitcoin.
Oh,
And that was my first exposure to your work. I watched this talk about quantum money
yeah.
that you gave. So
Yes.
I'm curious, like whether you can give an idea of whether do you think that's more feasible as like a personal thing, where instead of having a blockchain that tracks, who has sent what to whom, you just have these basically cash-like objects
So yeah.
that are
So
quantumly
okay,
secure,
good. So that's
but
another.
can be sent to people
Yes.
remotely.
Yeah. Yeah. So okay. So that's another major thing that I worked on. 15 years ago. And actually, I first heard about Bitcoin when I was giving talks about quantum money, in 2012 or so. And people kept saying, well, what about this new Bitcoin, this blockchain thing? Doesn't that solve the problem? And so, I had to explain my talks. Why, yes, you can use like the whole internet to fulfill the role that a trusted third party, would have. And that's a
Hmm.
really cool idea. But, it seems kind of impractical. It's, we're going to require this blockchain that just keeps growing without bound, surely.
Yeah, the massive
Yeah,
energy
yeah,
cost
yeah,
of
and right, and
of
this
maintaining the
right, that's
ledger.
right, and this massive energy expenditure. Surely, we eventually want a better solution than that. The thought never even crossed my mind that nevertheless I should just put my whole life savings into Bitcoin and keep it there. That's just not the. I guess it's good that I'm a professor and not an investor, right? But uh, so quantum money was actually a much older idea. It goes all the way back to a physicist named Stephen Wiesner in the late 1960s. Okay, and the idea here is that you would use quantum states as your, sort of unclonable cache. Right? So one of the basic facts in quantum mechanics is called the no cloning theorem. Right? It says that there is no physical procedure to reliably copy an unknown quantum state. Okay. And intuitively, the reason for that is like if I give you a quantum state, like you can make a measurement of it, but measurement in quantum mechanics is a destructive operation, right? It forces your qubit to decide, does it want to be a 0 or a 1, right? And it chooses an answer probabilistically, but then whichever answer it chooses, it then sticks with that, right? And all the remaining information about what the amplitudes were is then gone. Okay, so there's no cloning of arbitrary quantum states. And what Wiesner realized in the late 60s was that you could exploit that fact to make sort of physically unclonable cache. Okay, but his scheme had one major drawback, which was that the only way to verify the cache as authentic would be to bring it back to the bank that had minted it. Okay, and then that bank, would know the secret of how each qubit was prepared. Using that knowledge, it could measure the qubits in the appropriate way to check that yes, this really is good money. Okay, but if you have to bring the bill back to the bank to verify it, when it's like you haven't really cut out the middleman, right? The bank is still involved. Okay, and so if your real goal is to have currency that it requires no third party, then we haven't quite gotten there, right? And so then a bunch of us around 2009 or 2010 sort of revived the subject and started thinking about, could you have quantum money that anyone could verify, right? But that would, even if it wouldn't be physically impossible to copy, it would at least be intractable to copy. So like any quantum algorithm would need exponential time to counterfeit a bill. Okay, and I proposed several schemes for this publicly verifiable quantum money, some by myself, then one of them with my then student, Paul Cristiano, who has, by the way, since become a central figure in the field of AI alignment, right? But back then he was doing quantum computing with me, and we proposed this quantum money scheme. Unfortunately, most of the schemes that we proposed were then broken by various people, but then my and Cristiano's scheme was patched up in 2017 by Mark Jandry. Okay, and with that patch, the scheme is still standing today. Okay, so if we all had, and you're absolutely right, this would require that we all have personal quantum computers, right? Or
So what would that quantum computer look like? Like, what would that object look like to
I mean, I don't know.
fulfill the scheme that you put together?
Right now, if you walk into a quantum computing lab, what you see, well, it depends on the on which hardware platform that you.
Oh, but I guess let's say architecturally, like what how many qubits or what does it
Oh,
need to do?
okay. Well, it needs to do general quantum computation, right?
Okay.
Like at this point, like we might as well just talk about a general purpose quantum computer rather than building special things for each application. Okay, so um, so you would need to be able to do quantum computation on, let's say, many thousands of logical qubits, which once you use error correction, that may mean millions of physical qubits. And
So that's to maintain one wallet or one
you
like
maintain one
cache.
bill. I'm just talking about one bill right now. Okay. And you would also need to be able to transmit those qubits over the internet. So this would require upgrading the whole physical architecture of the internet. Okay.
And how does it work in terms of like you to store that bill? How do you store it? Like, what does it mean? How does it persist over time?
Yeah. So you would
Because the state will collapse.
yeah,
Like,
you would also need a way to store qubits persistently, keep them from losing their quantum state in your wallet. So these are major practical problems.
is there a way to combine like one central quantum computer and then many classical objects that people hold into some kind of hybrid system that would do this?
So there has been more recent work suggesting that you can do things like that. You could have the a quantum computer in one place, or just have one person holding the quantum computer, holding the quantum states, and they can then use that to answer challenges that prove that, like, yes, I do have this bill, I do have this money, right?
Yeah, so for example, you could put a quantum computer like into orbit, let's say, and then
Put
everybody
it
can
into
talk to it by
orbit.
satellite, or
Maybe,
something of that
yeah,
flavor.
yeah, or you could leave it on Earth. That might be easy.
Yeah, yeah, yeah.
Put it on the
Yeah,
cloud.
Well, I guess the idea is
yeah,
that like you want it to be permissionless, so you want it to be
that's right.
difficult to mess
No,
with,
that's right.
right?
That's right. And of course, there will then arise a question of, what if the server that is storing all this stuff is untrustworthy? Just like with cryptocurrency, it was all supposed to be trustless, but then in practice, the way that people did it was using these exchanges, right? And then,
Mm-hmm.
in
Mm-hmm.
practice, you really do need to trust the exchange that is holding your cryptocurrency for you. So
Is there a way to split it up? Like I have one qubit in my hand, and then the rest of them are on the server, for example.
possibly. Yeah, I mean, these are all things that are actively being thought about. I mean, there have also been proposals that would sort of hybridize um um quantum money with blockchain, and maybe get some of the advantages of both and have some of the drawbacks of both. So yeah,
Hmm.
these are all things that could be thought about. I mean, I think one thing that I would be more optimistic about for the near future would be just using quantum computers to just do like proof of various behaviors for just classical blockchains. Right. So
Hmm.
certified randomness would be one example where you can use a quantum computer to prove a certain behavior that is then useful, like in that case for proof of stake cryptocurrencies, like Ethereum, which do require certified randomness. I should have said, right? But there could be other kinds of protocols, like zero knowledge protocols, where you need to prove some behavior in some, possibly in some blockchain protocol, and you can use a quantum computer to do that. So I unfortunately I need to go soon, but I wanted to. There was one other question that I know I didn't get to, which was about what is beyond quantum computers, right? And so there is a conjecture or belief called the quantum extended church Turing thesis, which would say that every physical system can be efficiently simulated by a quantum computer. Now, the original extended church Turing thesis said that every physical system can be efficiently simulated by a classical computer, right? And most of us no longer believe that today. Why do we no longer believe it? Well, because we believe there can be quantum computers. But now, you could say, okay, look, once you've taken quantum mechanics into account, quantum mechanics was this massive change, to the laws of probability themselves, even, but that physics had to make 100 years ago. But once it made that, right, we have not seen a single exception to quantum mechanics for 100 years, right? We've never seen anything in nature that could not be described by quantum mechanics, right? The one thing that has not yet been fully reconciled with quantum mechanics is general relativity, right? But even that, at least the string theorists, believe that that should ultimately be subsumed into quantum mechanics, and there should be a theory of gravity that will just be quantum mechanical, where yes, general relativity will have to change, but quantum mechanics will not have to change, right? Because quantum mechanics seems almost impossible to modify without just producing nonsense, right? It's like a very, very rigid framework, okay? Uh, and so if quantum mechanics remains, the basic operating system for physics, and if, we don't discover something radically new about what can be built on top of quantum mechanics, right? Then I would tend to believe this quantum extended church Turing thesis, which would tell us that quantum computing is the end of the line in some sense, right? And, and that may seem incredibly short-sighted, right? because, aren't there always surprises, right? But I think the key is it's often hard to know in what direction is the next surprise going to come, right? Like people used to believe the Earth was flat. Okay, then they learned that it was approximately spherical, right? That doesn't mean that 1,000 years from now people will believe that the Earth is a torus or a Klein bottle or something like that, right? It was just, there was a right answer and we had to learn it and we did, right? So it could be like that. On the other hand, I keep an open mind. Maybe, someday we will discover that quantum mechanics itself is only an approximation to some other theory beyond it. And maybe that other theory would let us efficiently solve problems that not even a quantum computer could efficiently solve. Maybe the true complexity class of nature is something even larger than BQP. Of course,
Are there any naturally occurring quantum computers, like in space, for example? Can you
well,
send information to a black hole and get a computation back, for
okay,
example?
so sending something to a black hole, the problem is that any of the astrophysical black holes, the ones that we know about
Are far away.
from collapsed that are formed from collapsed stars, in order for the information to come out in the Hawking radiation, you'd need to wait like 10 to the 67th years or something like that. Okay, so
Or maybe you could like orbit it, for example. You could have light orbit it and come back at you, for example, and there's some
oh
information in it that
yeah,
computes
yeah.
something.
So it's not obvious that these things would be quantum computation. I mean, the closest thing that I know of to quantum computations in nature would simply be all the very complicated molecules and materials that come
Hmm.
across, right? That have equations that are extremely hard to solve because of
Mm.
exponentiality of their wave functions, right? And if you wanted to, you could think of all these systems as special purpose quantum computers that are just there to simulate themselves, as it were, right? So they're not programmable quantum computers, right?
Hmm.
But then again, we also didn't see much in the way of programmable classical computers in nature. We pretty much had to build them, right? The closest we found in nature, I would say, to a universal classical computer was our own brains.
Thank you,
But
Scott. That was a very beautiful
Thank you,
ending.
Scott.
yeah,
A
Thank you
great
very
absolutely.
much.
conversation.